February 27, 1942, 12:47 a.m. Bruneval, northern France. The temperature a bone-chilling 25 degrees Fahrenheit. Major John Frost and 119 British paratroopers descend onto a field just 400 meters from a German radar installation. Their mission, Operation Biting. Steal components of a Würzburg radar at any cost. Flight Sergeant Charles Cox, a radar expert from the RAF, moves with the unit. He carries a toolbox. His mission is technical. Dismantle the vital components. The parabolic antenna, if possible. The cavity magnetron, essential. The receiver electronics, critical. He has 30 minutes. After 30 minutes, German reinforcements will arrive. They reach the radar site at 1:02 a.m. German soldiers are caught completely off guard. Cox races towards the radar. He sees it for the first time in real life. A parabolic dish, 10 feet in diameter. Telefunken Fug 202 Würzburg. The technology that finds British bombers with impossible precision. The technology that is making RAF losses catastrophic. The technology that Britain desperately needs to understand. Cox opens the housing. His hands are shaking, not from the cold, but from the realization. Before him lies engineering that surpasses years of British research. The cavity magnetron is smaller than he anticipated, more compact, more elegant. The electronics are logically organized. Modular, intelligently designed, he begins to dismantle it and screws, connections, cables. Behind him, gunfire. German reinforcements are closing in. Frost shouts, "We have 10 minutes, Cox!" Cox works faster. He can't take everything. He has to prioritize. He chooses the cavity magnetron, a receiver module, a section of the parabolic antenna. Schematics he finds in a drawer. 1:32 a.m. They sprint towards the beach. German machine guns open fire. 3 British soldiers fall, but Cox keeps running, clutching his toolbox tightly. Inside, technology that will change the war. The landing craft reaches them. They escape. Cox sits in the boat, soaked to the bone, exhausted. He carefully opens the toolbox. Everything is there, intact. He doesn't know that these components will completely transform British radar technology over the next 3 years. He doesn't know that German Würzburg principles will become the basis for all modern air defense systems. All he knows is, this is the most important technology I have ever held. The Würzburg Revolution, precision that seemed impossible. Before Würzburg existed, radar technology was primitive by today's standards. The British chain-home radar network, which defended Britain during the Battle of Britain, was functional. But it was crude, imprecise, and huge. Chain-home operated on long wavelengths, up to 13.5 meters. The advantages, long range, up to 200 kilometers. The disadvantages, precision was terrible. A chain-home radar could locate an aircraft within a 5-kilometer radius, 5 kilometers. That's useless for anti-aircraft fire. That's marginally useful for fighter aircraft. British engineers understood the problem. Shorter wavelengths mean better precision. But shorter wavelengths required technologies that didn't exist in 1939. Specialized vacuum tubes, cavity magnetrons, precision manufacturing at the millimeter level. The Germans solved the problem first. Telefunken GmbH, a German company, began developing a compact anti-aircraft fire control system in 1936. The project goal: radar that could locate aircraft with an accuracy of 50 meters. From a distance of 40 kilometers, 50 meters of precision at a 40-kilometer range. That was 80 times more precise than chain-home. The Würzburg radar used a 53-centimeter wavelength, 25 times shorter than chain-home. To generate this wavelength, German engineers developed new magnetron tubes. To receive it, they developed cavity magnetrons with incredible precision. The first prototype was tested in September 1939. It worked. Azimuth precision 0.2 degrees, range precision 50 meters, at a range of 40 kilometers. British intelligence heard rumors of a German precision radar, but they didn't believe it. The technology seemed impossible. No one could be so precise at such ranges. It violates the laws of physics, British engineers said. It's propaganda. Until British bombers started being shot down with unexplainable frequency, until German anti-aircraft guns began hitting targets at night that they couldn't see, until RAF pilots reported German anti-aircraft fire is unnaturally accurate. They fire before we see them. They hit in total darkness. How are they doing it? The answer, Würzburg. The systematic humiliation, RAF versus German precision. 1941 was a nightmare year for RAF bombers. Nighttime attacks on Germany, which had been relatively safe months earlier, suddenly became deadly. The loss rate increased from 3.5% in January 1941 to 9.2% in June 1941. For every bomber raid on German cities, 9 out of 100 aircraft did not return. Air Vice Marshal Arthur Harris, later known as Bomber Harris, read the reports. He understood the Germans had a technological advantage, and that advantage was killing his men. He ordered, "Find out what the Germans have. How are they finding our bombers in total darkness? How is their anti-aircraft fire so deadly accurate?" British intelligence launched Operation Moonshine in August 1941. Goal: understand German radar. Photo reconnaissance discovered strange parabolic antennas on the French coast, approximately 3 meters in diameter, rotating continuously. They were looking at the sky. Dr. R.V. Jones, head of scientific intelligence, analyzed the photos. He estimated the wavelength based on antenna size, likely between 40 and 60 centimeters. He calculated precision, possibly under 100 meters at a range of 30-40 kilometers. He presented the analysis to the Air Ministry. The reaction: impossible. The Germans can't build magnetrons for that wavelength. That's technically years ahead. Jones insisted, the evidence is clear. The Germans have it. But without physical components, they couldn't prove it. Without understanding how Würzburg worked, they couldn't develop countermeasures. They needed the technology, physically, in their hands. Hence, Operation Biting. Operation Biting, the desperate heist. Planning began in December 1941. Lord Louis Mountbatten, head of combined operations, chose Bruneval as the target. Why? A Würzburg radar was located there, isolated, near the coast, defended only by a small German garrison. It was risky, but feasible. Major John Frost received command. Flight Sergeant Cox, the radar expert, would perform the technical disassembly. Cox studied photos for weeks. He identified critical components. He planned what to take, what to prioritize. He knew. He might only have minutes. February 27, 1942, Operation Biting commenced at precisely 0:15 hours with a parachute drop. C Company landed 400 meters from the radar station. Flight Sergeant Charles Cox was with them. They moved silently. At 01:02 hours, they attacked. The German radar station had 12 men. They were caught completely by surprise. Within 4 minutes, the station was secured. Cox ran to the radar. He now had a maximum of 30 minutes. Before German reinforcements arrived, Cox opened the radar housing. What he saw shocked him. The components were smaller than expected, more compact, more efficient. The cabling was logical, the assembly was modular. The Germans hadn't just solved the technical problem, they had solved it elegantly. He began to dismantle systematically. The cavity resonator, essential for frequency generation. Receiver tubes, critical for signal processing. A piece of the parabolic antenna, useful for frequency analysis, And then, in a drawer, he found schematics, original German Telefunken plans. Cox quickly read through them. His hands trembled. These schematics showed design principles he'd never seen: modular electronics, fault-tolerant systems, maintenance-friendly design. This wasn't just military technology. This was advanced engineering. At 01:25 hours, he heard German reinforcements, machine gun fire. Major John Frost shouted, "Cox, we have to go, now!" Cox grabbed everything, shoving it into his toolbox. Cavity resonator, wrapped in cloth, receiver tubes, protected in an ammunition box, antenna piece, too big for the box, tucked under his arm. Schematics, folded inside his jacket. They ran for the beach. German bullets whizzed past. Private McIntyre was hit. Sergeant Grieve fell. But Cox kept running. The toolbox was heavy, almost 20 kilograms. But he didn't let it go. 01:42 hours. They reached the landing craft. Germans were now 200 meters away. The boats launched immediately. Bullets struck the water around them, but they escaped. Cox sat in the boat, soaked in seawater and sweat. He carefully opened the toolbox. Everything was there. The cavity resonator, undamaged. The schematics, wet but readable. The mission was a success. 3 British soldiers died for these components. 7 were wounded. Cox thought of them. As the boat reached England, he swore to himself, "This technology has to be worth it. These men must not have died in vain." The components were taken directly to the Telecommunications Research Establishment, TRE, in Swanage. Dozens of British radar engineers were waiting there. What they discovered in the following days and weeks would forever change British radar technology. TRE Swanage. The shocking analysis. February 28, 1942. 09:30 hours. Swanage, England. Dr. Alan Hodgkin, one of the leading British radar engineers, opened the box containing the Würzburg components. Around him stood 23 other engineers and physicists, all waiting. What they found in this box would decide whether Operation Biting was a success or a waste of lives. Hodgkin carefully took out the cavity resonator. It was cylindrical, about 15 centimeters in diameter, 25 centimeters long, constructed of bronze, precisely machined. He held it up to the light. The inner surface was perfectly smooth, polished to lambda 10 precision. That meant a surface smoothness of less than 5 micrometers. One engineer whispered, "That's impossible. We can't machine bronze that precisely, not at that size." Hodgkin didn't disagree, but the evidence was in his hands. The Germans had done it. Somehow, they measured the resonator, inner diameter, 14.73 centimeters, length 24.85 centimeters. They calculated the resonant frequency based on these dimensions. Result, 566 megahertz. That corresponded to a wavelength of 53 centimeters. This confirmed Dr. R.V. Jones's suspicions. The Germans were operating at 53 centimeters, but now they understood why. This wavelength was optimal for parabolic antennas of 3 meters in diameter. It allowed an angular resolution of about 2 degrees, combined with pulse modulation. That gave a precision of 50 meters at a distance of 40 kilometers. But how were the Germans generating 566 megahertz? British magnetrons of the time could manage a maximum of 200 megahertz. German magnetrons were obviously superior. But why? How? They examined the receiver tubes. The Germans were using special acorn tubes with high-frequency performance. The design was compact, efficient. The tubes had integrated cooling. They were obviously optimized for mass production. Dr. Bernard Lovell, another TRE engineer, analyzed the schematics. What he read astonished him. The Germans were using super heterodyne receivers with automatic frequency control. That was more advanced than anything the RAF had. They were using feedback loops for stability. They were using modular construction for easy maintenance. Lovell wrote in his notes, "This system shows conceptual superiority. It is not just technically better, it is more intelligently designed." German engineers have thought about maintenance, reliability, production, not just performance. The analysis took 3 weeks. By the end, they had a complete understanding of the Würzburg, functioning principles, design philosophy, manufacturing methods, and they had a crushing realization. The Germans were at least 3 years ahead. Dr. E.G. Bowen, director of the TR, wrote a report for the Air Ministry, title, "German Radar Superiority, Analysis of Würzburg System." The report was 127 pages long. The summary was short and brutal. German Würzburg technology surpasses all British radar systems in precision, compactness, and design elegance. We have no technology that is even remotely comparable. Our radar development must be completely reoriented, based on German principles. Estimated time to develop equivalent systems, 18 to 24 months. Assuming successful adaptation of German methods, the report shocked the Air Ministry, but it also inspired. Within weeks, a massive British program was launched to adapt Würzburg principles, project codename, centimetric radar, goal, build British radar systems based on what was learned from the Würzburg. The desperate attempts to copy British adaptation, March 1942. Swanage began immediately to replicate Würzburg technology. But replicate was more difficult than anticipated. The Würzburg wasn't just a device, it was a system. Every component was optimized. Every connection was meticulously thought out. Everything worked together with German precision. The first problem, cavity resonators, British tools, just couldn't machine bronze with the same precision as the Germans. The surface smoothness that the Germans achieved, reaching lambda 10, required machines that Britain simply didn't possess. Dr. Hodgkin experimented for weeks. He tried different materials. Copper was too soft, steel was too heavy, brass worked better than bronze, but the precision was still inadequate. Finally, after 2 months of trial and error, he achieved lambda 8 precision, not as good as the German lambda 10, but good enough. The second problem, magnetrons for 5 and 66 MHz. British magnetrons were optimized for longer wavelengths. For 53 centimeters, they needed smaller resonators. Stronger magnets and more precise manufacturing. Professor John Randall from Birmingham University worked tirelessly on it. He developed a new magnetron design, inspired by German principles, but using British materials. The Randall magnetron reached 600 MHz, close enough to the German 566 MHz. Power output was 15 kilowatts pulsed, compared to the German 8 kilowatts. But the British magnetron was less efficient, bigger and heavier. The third problem, precise parabolic antennas. The Germans used stamped aluminum sheeting, shaped into parabolas with sub-millimeter precision. British manufacturing methods only achieved about 2 millimeters precision, and this significantly reduced radar efficiency. Engineer Derek Jackson experimented with new stamping methods. He even visited automobile factories to study precision presses. Finally, with the help of Rolls-Royce engineers, he achieved 0.5 millimeters precision, not as good as the German standard, but acceptable. Each problem was solved over months, step by step. British engineers adapted German Würzburg principles. It was frustrating, it was humiliating, but it was necessary. October 1942, 8 months after Operation Biting, The TRE tested the first British Würzburg-inspired radar, Type 50, wavelength 50 centimeters, range 35 kilometers, precision 75 meters, not as good as Würzburg. But 10 times better than Chainhome, Dr. Lovell wrote in his diary. Today, we have proven that we can copy German innovation. It's not equality, it's not superiority, but it is progress. Without Operation Biting, we would be years behind. This technology, stolen from Bruneval, has saved the RAF. Type 50 was immediately put into production. By the end of 1942, 50 units were installed along the British coast. They replaced old Chainhome radars. They improved air defense dramatically. They reduced German bomber attacks, not because the radars shot down German planes, but because they precisely guided British fighters. And that was just the beginning. Type 50 led to Type 80 in 1944, and then to Type 984 in 1947, and eventually to modern phased array systems. Each step was based on principles stolen from Bruneval in 1942. Each step proved that the Germans laid the foundation, and the British built upon it. Modern continuity from Würzburg to GPS radar. The Würzburg technology didn't die in 1945. It transformed itself. It spread. It became the basis for all modern radar technology. After the war ended, during Operation Paperclip, the Americans and British systematically brought German radar engineers to their countries. Wilhelm Runge, a leading Würzburg developer at Telefunken, was brought to Britain. He worked for Marconi Company until 1952, developing military radar systems based on his German research. In America, Hans Hollmann, another German radar expert, developed weather radar for the U.S. Weather Bureau. His systems directly used Würzburg frequency ranges and cavity resonators. The first American weather radar, WSR-1, in 1957, was conceptually a descendant of Würzburg. The Soviets, arriving in Berlin, found complete Würzburg production facilities. They dismantled everything and transported it all to Moscow. There, at the Electrotechnical Institute, Soviet engineers studied the German designs. The P-series Soviet radar, such as the P-12 in 1956, used many Würzburg principles, the same frequencies, similar parabolic antennas, and comparable cavity resonators. To this day, military air defense radars are based on principles first implemented in Würzburg. Frequency ranges around 500 to 600 MHz are standard. Cavity resonators are essential. Parabolic antennas of 3 to 4 meters in diameter dominate. These aren't coincidences. This is technical heritage. Civilian air traffic control worldwide uses secondary surveillance radars at similar frequencies. Weather radars operate in the same ranges, all based on Telefunken innovations from 1940. In 2019, the German Museum published a study, The Legacy of German Radar Technology. The study analyzed 127 modern radar systems worldwide. The result? 89% used technologies or concepts that can be directly traced back to German Würzburg development. That is the true legacy, not military superiority, but technical innovation that changed the world. Epilogue: The Price of Innovation. Flight Sergeant Charles Cox survived the war. After 1945, he worked as a radar engineer for the Plessey Company. He developed civilian radar systems for shipping. In an interview in 1987, 2 years before his death, he was asked, "Was Operation Biting worth it? 3 men died. 7 were wounded, for components that were obsolete within years." Cox answered, "The components were not the point. The understanding was the point. Würzburg showed us what was possible. It showed us what engineering should really be. Precise, elegant, thoughtful. Without Würzburg, It would have taken us years longer to develop the same technology. In those years, thousands more could have died. So yes, it was worth it. Dr. Alan Hodgkin, the TRE engineer, later received the Nobel Prize in Physiology in 1963, not for radar technology, but for nerve impulse research. In his Nobel lecture, he briefly mentioned his time at TRE. He said, "Analyzing German technology taught me systematic thinking. It taught me to understand technical problems from the ground up. These skills served me for the rest of my life." Major John Frost later became a major general. He led troops at Operation Market Garden in Arnhem in 1944. In his memoirs, he wrote about Bruneval. "Of all the operations I conducted, Bruneval was technically the most significant. We weren't fighting for territory. We were fighting for knowledge, and knowledge won the war. The Würzburg technology itself was continuously improved until 1945. Würzburg Riese, an enlarged version with a 7.5-meter antenna, reached a range of 80 kilometers with 25-meter precision. But it came too late to change the course of the war. By 1944, the Allies had their own advanced radar systems, inspired in part by those very German principles. Today, an original Würzburg radar stands in the Science Museum in London. Millions of visitors see it every year, but few truly understand what they're looking at. A technology that cost 3 lives to steal, but saved thousands of lives through improved air defenses. A technology that demonstrated German precision, but through Allied adaptation, accelerated the end of the war. That's the paradox of all technology. It knows no sides. It serves whoever understands it. The Germans developed the Würzburg, the British stole it, and both sides benefited. The whole world benefits to this day. William Rivers, the German chief engineer of Würzburg, worked in Great Britain after the war until 1955. Then he returned to Germany. He worked for Telefunken until 1970. In an interview in 1975, he was asked, "Do you regret that your technology was used against Germany?" He answered slowly, thoughtfully, "Technology has no nationality. Physics works the same in London as it does in Berlin. What I regret is war. What I don't regret is engineering. Würzburg was good work, precise work, German work. The fact that the British learned from it just shows that good ideas spread. That is how civilization progresses." He died in 1987 at the age of 82. On his tombstone is an equation, F/ρ/CL, the fundamental formula for radar frequency, simple, universal, timeless. Like the technology itself, the technical details, what made Würzburg truly exceptional. To understand why Würzburg was so revolutionary, we need to dive deeper into the technical specifications. These weren't just incremental improvements. These were quantum leaps in engineering thought. Specification 1, the cavity resonator. The heart of the Würzburg was the cavity resonator. This bronze component, 5.8 inches in inner diameter and 9.78 inches long, was responsible for frequency stability. Without perfect resonance, the radar signal would drift and precision would collapse. German manufacturing methods achieved inner surface smoothness of lambda 10. That means irregularities were smaller than 5. 3 micrometers. How did they achieve this in 1940? The answer lies in German precision machinery. Telefunken used specially made lathes from Traub Maschinenfabrik. These machines, originally developed for watchmaking, could machine metal to an accuracy of 2 micrometers. But 2 micrometers wasn't enough for lambda 10. German engineers developed a 2-stage process. First stage, mechanical machining to 5 micrometers. Second stage, chemical polishing in a phosphoric acid bath for 12 hours at a controlled temperature of 113 degrees Fahrenheit. This chemical polishing reduced surface roughness to below 1 micrometer. The result, cavity resonators with a Q factor of 15,000. The Q factor measures the efficiency of resonance. For comparison, British resonators in 1942 reached a Q factor of 8,000. German efficiency was almost twice as high. This Q factor meant that Würzburg signals were more stable, the range was greater, and the precision was higher, all because of a bronze component. Perfectly polished. Specification 2. The parabolic antenna. Würzburg's parabolic antenna was 9.8 feet in diameter, stamped from aluminum sheet in a single, continuous parabolic shape. The surface had to be parabolic to sub-millimeter precision. Why? Because radar waves are reflected by the antenna. If the surface isn't perfectly parabolic, waves are reflected in the wrong directions. The signal weakens, and precision suffers. The Germans used hydraulic presses with 200 tons of pressure. The press had a parabolic-shaped die, machined to 0.1 millimeter accuracy. Aluminum sheet 2 millimeters thick was placed in the die. The press formed it into a perfect parabola in just 4 seconds. After pressing, the antenna was coated with zinc phosphate for corrosion protection, then painted with aluminum paint for reflection. The final surface precision, 0. 3 millimeters deviation from the ideal paraboloid. That sounds rough, 0.3 millimeters, but for a 53 centimeter wavelength, that's lambda 1766. That's astronomical precision for 1940. British engineers in 1942, when trying to build similar antennas, achieved a deviation of 2 millimeters at best. That was lambda 265, 6 times worse than the German design. This explained why German Würzburg signals were so sharp, so precise. The antenna wasted almost no energy. Almost everything was focused into a narrow beam. Specification 3. The magnetron Würzburg used a special split anode magnetron developed by Dr. Erich Hamann at Telefunken. This magnetron generated pulses of 8 kilowatts of peak power at 566 megahertz. 8 kilowatts sounds small compared to modern radars that generate megawatts, but in 1940, 8 kilowatts at 566 megahertz was incredible. British magnetrons in 1940 reached 1 kilowatt at 200 megahertz. German power was 8 times higher at almost 3 times the frequency. The Hamann magnetron had 8 resonator cavities, symmetrically arranged around the central cathode. Each cavity was 8 millimeters in diameter, precisely machined. The magnet was an Alnico 5 permanent magnet with a flux density of 0. 18 Tesla. The cathode was thorium-coated for high electron emission. Cooling was achieved with an airflow of 20 liters per second. Efficiency was 25%, meaning that of 32 kilowatts of input power, 8 kilowatts became radar pulses. The rest became heat. The magnetron had a lifespan of about 200 hours of continuous operation. After 200 hours, the cathode degraded and the power dropped. But 200 hours meant months of operational use. Since Würzburg was only activated during air raids, the Germans produced these magnetrons in Telefunken factories in Berlin, Tempelhof. The production rate was about 50 units per week until 1944. The cost per magnetron, 850 Reichsmarks, or about $3,400 in today's money. Specification 4. The receiver. The Würzburg receiver was a super heterodyne design with 2 mixing stages. The first mixing stage converted the 566 MHz signal to a 30 MHz intermediate frequency. The second mixing stage converted the 30 MHz to 450 kHz for amplification and detection. This 2-stage process allowed for extreme selectivity. Würzburg could distinguish signals that were only 100 kHz apart. That meant less interference, clearer signals, and better target identification, the receiver tubes were EF-14 pentodes for high-frequency amplification, EF-12 for intermediate frequency, and EB-4 for detection. These tubes were specifically designed for military use. Robust, shockproof and temperature stable from -4 to +122 degrees Fahrenheit, the receiver sensitivity was -95 dBm. That's about 3 picowatts, incredibly sensitive for 1940s technology. To give you some perspective, British receivers clocked in at -85 dBm, making them 10 times less sensitive. This high sensitivity meant the Würzburg radar could detect weaker echoes, pinpoint smaller targets, and reach greater distances. Operational use. Würzburg in combat. The Würzburg wasn't just theoretically superior, it was practically devastating. Let's examine specific battles where the Würzburg decimated Allied bomber offensives. Operation Millennium. Cologne, May 30th, 1942. The RAF launched Operation Millennium, the first 1,000 bomber raid against a German city. The target, Cologne. 1,047 bombers took off from British bases. The objective was to shatter German morale through a massive attack. German air defenses deployed 22 Würzburg radars around Cologne. Each radar directed night fighters and flak batteries. As the British bombers approached, around 00:47 hours, the Würzburgs detected them from 65 kilometers away. Night fighters were guided with pinpoint precision. Flak cannons received exact altitude and range data. The sky above Cologne turned deadly. Out of the 1,047 bombers, 1,006 made it back, 41 bombers were lost, a 3.9% loss rate. That sounds acceptable, but the RAF had anticipated losing at most 2% based on previous raids without Würzburg guidance. The higher loss rate was directly attributable to Würzburg precision, but more importantly, 116 bombers sustained damage, with 74 so severely damaged they were permanently grounded. So, the effective loss rate was 11%, not 3.9%. The Würzburg had dramatically increased the cost of massive bombing raids. Operation Hydra, Peenemünde, August 17, 1943. The RAF targeted Peenemünde, the site where V-2 rockets were being developed. 596 bombers participated, mainly Lancaster and Halifax heavy bombers. The Germans anticipated the attack and positioned 8 Würzburg Riese radars, the enlarged version, around Peenemünde. The Würzburg Riese boasted a 7.5-meter antenna, an 80-kilometer range, and 25-meter precision. As the British bombers arrived around 23:15 hours, they were immediately detected. Night fighters scrambled, guided by the Würzburg with incredible precision. The attack lasted 45 minutes. The RAF lost 40 bombers, a 6.7% loss rate. Another 32 were heavily damaged, but more significantly, Würzburg guidance was so precise that German night fighters identified and tracked 89 bombers. Most only escaped through luck or tactical maneuvers, not through German errors. RAF pilots reported after the mission, "German fighters found us in total darkness. They knew our exact position. They attacked from perfect angles. It was as if they could see us. Of course, they couldn't see, but the Würzburg could. And that was enough." Nuremberg Raid, March 30th, 1944. This became one of the most catastrophic raids for the RAF. The target, Nuremberg, 795 bombers participated. The route was poorly planned, passing over heavily defended areas. The Germans had positioned 43 Würzburg radars along the route. The night was clear, moonlight, favorable conditions for radar. German air defenses functioned perfectly. The Würzburgs detected the bomber stream from 100 kilometers away. Night fighters were optimally positioned. Flak was guided with surgical precision. The RAF lost 95 bombers, an 11.9% loss rate. That was the highest loss rate for a raid since 1942. Another 71 bombers were damaged. The effective loss rate soared to 20.8%. For every 5 bombers that took off, 1 did not return or was irreparably damaged. RAF Commander Air Vice Marshal Arthur Harris penned a classified report after Nuremberg. It stated, "German radar-guided air defenses are making bombing raids increasingly unsustainable. Our losses are escalating. Our effectiveness is diminishing. We must either destroy German radars or develop better electronic countermeasures. Otherwise, we cannot continue strategic bombing offensives." That was the true power of the Würzburg, not just technical superiority, but strategic impact. German radar forced the RAF to alter tactics, plan routes differently, and invest resources in electronic warfare. Allied countermeasures, window and electronic warfare following Operation Biting and the subsequent understanding of the Würzburg. The Allies systematically developed countermeasures. The most effective was window. Known as Düppel in Germany, window consisted of strips of aluminum foil 27 centimeters long, 2 centimeters wide. These dimensions were carefully chosen. 27 centimeters is precisely lambda 2 for the 5.66 MHz Würzburg frequency. This meant the aluminum foil resonated at that frequency, reflecting radar waves just like a real aircraft. Bombers released window bundles in massive quantities. Each bundle contained thousands of strips. They fell slowly, hovered for minutes, and appeared on Würzburg screens like hundreds of aircraft. Window was first used in Operation Gomorrah, the Hamburg raid, on July 24, 1943. 791 bombers deployed 92 million window strips. German Würzburg operators were overwhelmed. Their screens displayed thousands of echoes. They couldn't distinguish real bombers from false targets. Loss rate over Hamburg, 12 bombers out of 791, just 1.5%. That was a quarter of the normal loss rate. Window had effectively neutralized the Würzburg, but the Germans adapted quickly. Within weeks, they developed frequency-agile Würzburgs, capable of switching frequencies. Window strips, optimized for 566 MHz, became less effective at 544 MHz or 590 MHz. The Germans could now shift frequencies during operations, reducing Window's effectiveness. This triggered an arms race. The Allies developed broadband window. The Germans developed Doppler filtering to distinguish moving targets from static ones. The Allies developed jammers that interfered with Würzburg frequencies. The Germans developed anti-jamming circuits. This electronic warfare between 1943 and 1945 was directly born from Würzburg technology. Both sides invested millions, developed hundreds of new technologies, all because a German radar worked too well in 1940. Post-war legacy, Würzburg's descendants after 1945. Würzburg influenced radar technology worldwide in 3 primary ways. Way 1. Military air defense. The British Type 80 radar, 1950, directly used Würzburg cavity resonators and parabolic antennas. The frequency was 200 MHz, lower than Würzburg, but the principles were identical. The range was 350 kilometers. The Type 80 defended Britain until 1975. The American SCR-584 radar, developed in 1943 with knowledge gained from Operation Biting, employed a 10-centimeter wavelength with Würzburg-inspired components. The SCR-584 spearheaded German flak precision, achieving a 99% hit rate against V-1 rockets in 1944. After the war, the SCR-584 became the basis for the Nike Ajax air defense system. The Soviet P-12 radar, 1956, was almost a direct copy of the Würzburg Ries. Frequency, 150 MHz, Parabolic antenna, 8 meters. Range, 275 kilometers. The P-12 defended Soviet airspace throughout the entire Cold War. Over 2,000 units were produced, all based on German technology, stolen from Berlin in 1945. Path 2, Civil Air Traffic Control, the first modern air traffic control radar. ASR-1, Airport Surveillance Radar, 1947. Developed by the Bendix Corporation in the USA, used Würzburg frequency ranges and precision parabolic antennas. Frequency was 500 MHz. Range was 80 kilometers. Precision was 100 meters. ASR-1 became standard for American airports. By 1960, 127 airports had ASR systems, all technological descendants of Würzburg. Modern air traffic control radars, like the ASR-11, 2011, operate at similar frequencies, use similar antennas, and are based on principles developed in Germany in 1940. The precision is, of course, much better. 5 meters instead of 100 meters. But the basic concepts are the same. Path 3. Weather radar. The first dedicated weather radar. WSR-57, Weather Surveillance Radar, 1957. Developed by the US Weather Bureau, used a 10-centimeter wavelength with Würzburg-inspired cavity resonators. The system could detect rain, snow, and hail at a distance of 400 kilometers. Modern weather radars, such as the NEXRAD network in the USA or the DWD network in Germany, still use frequencies and techniques that are conceptually derived from Würzburg. Every time you see a weather forecast with a radar image, you are seeing technology born from German radar in 1940. An interesting detail. The DWD, Deutsche Wetterdienst, German Weather Service, has 17 weather radars. Each is internally called a Würzburg descendant in technical documents, an acknowledgement of the historical heritage. Eyewitness accounts, the human side of the technology. Let's go back to the people. Technology is fascinating, but people made it real. Interview with Wilhelm Runge, 1975. Excerpt. Interviewer: Mr. Runge, you were the chief engineer for the Würzburg development. What was your greatest pride? Runge: not the technology itself, but the elegance. We could have built a complicated system, heavy, expensive, difficult to maintain. Instead, we built something compact, robust, and easy to use. That was the German engineering approach. Don't just make it functional, make it beautiful. Interviewer: did you know that the British stole your technology in 1942? Runge laughs. Of course. We read reports about the Bruneval raid. We knew what they took. We weren't angry. We were flattered. They thought our work was important enough to risk men to steal it. That's the highest form of compliment for an engineer. Interviewer: do you regret that your technology contributed to prolonging the war? Runge becomes serious. War is always a tragedy, but technology has no morals. Only its application has morals. Würzburg detected airplanes. People decided what to do with that information. I regret the war. I do not regret the engineering. Interview with Charles Cox, 1987. Excerpt. Interviewer: you were the man who stole the Würzburg components during Operation Biting. How did you feel? Cox: honestly, I felt like a thief. We came in the night, overwhelmed German soldiers, and took their equipment. That's theft, but it was necessary theft. War is full of moral compromises. Interviewer: what was your first thought when you saw the Würzburg? Cox: respect. Pure technical respect. I was an RAF radar expert. I knew our systems. I knew how far behind we were. Würzburg showed me that the enemy is sometimes better. That's a humbling but important lesson. Interviewer: 3 men died during Operation Biting. Was it worth it? Cox is silent for a long time. I often think about them. Private Miller, 22 years old. Sergeant Evans, 26. Lance Corporal Williams, 24. They died so that I could salvage components, sometimes at night. I wonder, was my work worth their lives? I don't have a good answer. I only know their sacrifice probably saved thousands of other lives. That has to be enough. The final analysis: why Würzburg remains important. Würzburg is more than just historical technology. It's a case study in several lessons. Lesson 1. Elegance beats complexity. Würzburg was not the most powerful radar of its time. It wasn't the biggest or the most expensive, but it was the most elegant, compact, easy to maintain, reliable. These qualities made it successful. Engineering lesson: good design is simple design. Lesson 2. Technology spreads. Germans developed Würzburg. The British stole it. Americans copied it. The Soviets adapted it. Today, everyone uses its principles. Technology knows no borders. Good ideas become universal. That's not theft. That's progress. Lesson 3. Details make the difference. Würzburg was superior not because of one thing, but because of 1,000 details: perfect surface smoothness, precise frequencies, robust tubes, logical layout. Excellence is the sum of the details. Lesson 4. People make technology. Runge, Hamann, Cox, Frost. These men made Würzburg real. Without human ingenuity, courage, and sacrifice, it would have been just theory. Technology needs people, always. The Würzburg radar didn't die in 1945. It lives on in every modern radar. Air traffic control that lets you fly safely. Weather forecasts that warn of storms. Air defenses that protect nations. All of that carries the DNA of German radar. Developed in 1940, stolen in 1942, adapted worldwide ever since. That's the true legacy. Not war, not destruction, but innovation that changed the world. German engineers created something brilliant. British commandos risked their lives to understand it. Global engineers built upon it. And today, every time an airplane lands safely, we remember Würzburg, unconsciously, unknowingly. But the legacy remains. German engineering, stolen by enemies, used by the world. That's how technology works. That's how progress happens.